Okay, I'm Norman Koren. I'm the creator of Imatest software. I'd like to thank Dick Lyon and Gary Embler for inviting me. It's quite a thrill to be here in the center of the high-tech, AKA geek world. And I also want to thank Google for making it possible for me to do this business because as a small entrepreneur with not much in the way of an advertising budget, Google has enabled me to communicate ideas to my potential customers and other interested people. I'm sure there are hundreds of thousands of small entrepreneurs around the world who are creating businesses that they couldn't have created without Google. So I'm very appreciative of that. Anyway, I'm going to be discussing Imatest software that I've developed for measuring image quality in any sort of digital imaging system, most commonly digital cameras, but it also works with scanners, scanned film images, and other devices. I'll talk a bit about the background of Imatest, how I got there. Then I'm going to go through a number of the key image quality factors and how they're measured. And then I'll review the same material discussing the Imatest modules. It's a modular program that analyzes a number of test charts, and I'll kind of go back over that material. Here is an example from the internet of an image that clearly has quality problems. I chose it because this is a building that I worked in for a while in Boulder. It's the Department of Commerce NIST building that contains the world's master clock, and I had an office for a while down the hall from it. I always used to think every time somebody would say, oh, I wish they could turn back the clock, I'd think, if only I could hack that clock down the hallway, but I'm not that good. In any case, this image shows a number of image quality issues, and these are typical of the sort of issues that we want to be able to diagnose and predict from testing. And so it's not, let's see if I can make this, here we go, not real clear, but there are some vertical lines here that could be flare light. I'm in fact not, well, you can see it above the car clearly. I'm not sure what the source of those lines are. The sharpness is generally poor in this image. There are some JPEG artifacts. These are waviness near boundaries. It's easier to see on a laptop screen. And there's very poor tonal detail in the shadow areas here. The question is this detail being captured? It's affected by response curve and flare light. And if it is captured, you may want to do some post-processing enhancement on it. So anyway, this is an image with a number of issues. I created Imatest really to measure and predict system performance and to answer questions about, for example, which lens is a better lens that photography nuts have been arguing over forever. I decided I needed a way of answering that question. The way that Imatest works is you photograph a test chart and then you analyze it with the Imatest software. And I have a bunch of examples, some fairly pretty, of what I do. One example is you can photograph the Grotag-Macbeth color checker in a scene, and then you can analyze the color checker to see how the camera's white balance algorithm and also how its exposure algorithm is working. But I have a number of other test charts, and I'll be going through several of those during the course of the talk. In fact, I created Imatest for serious amateur photographers. I thought that's where the market would be, and I was quite wrong, which turned out to be a good thing. Yeah, I thought it would be for us guys with digital SLRs who have collections of lenses, and we would want to find out which lenses are best and under which conditions, which focal lengths and which apertures they work the best. So the original version of Imatest was designed to look at camera response curve or dynamic range, sharpness, and color accuracy. Then I found it was being purchased mainly by corporate customers, which is a good thing. And I've gradually adapted to their needs, although I still have an Imatest Lite version that meets the needs of serious amateur photographers. The program runs in compiled MATLAB. You don't need MATLAB on your computer because it comes with a library. It's downloaded from imatest.com and sold online. And it consists of a number of independent modules that each of which measures a test chart. And what I try to do is extract the greatest information from each test chart. And I find that I'm constantly developing it, adding support for new charts, new image quality measurements. About half the ideas come from my head and half come from customers, probably the better half from customers. Now in the talk, I'm going to use an image I took from a wonderful place called Hunts Mesa in Monument Valley as an example of image quality degradations. I'm not sure how clearly it'll show up on this screen, but in the PowerPoint it should be quite clear. And what I do is on the crop of the image on the left side, I have the original image. That always stays the same. On the right side, I have a simulated image quality degradation that I use to discuss what this particular issue is. Some of the things we have to think about when we're talking about image quality are, is the quality factor mainly a function of image capture, meaning how the chip performs and the electronics coming out of the chip, or is it a matter of post-processing, which would include everything out of the chip, including demosaicing and any sort of contrast adjustments, sharpening, and so on, white balance that happen after the imaging chip. Another issue that I'm going to skirt is the issue of objective measurements versus subjective judgment, which is to say I have a number of objective measurements, sharpness, noise, color accuracy, and so on. I have some information on how they relate to how customers or clients will respond to that image, but that's quite a complex and difficult subject. For one thing, different customers are going to perceive image quality quite differently. So somebody who's doing aerial reconnaissance is looking at very different things from somebody photographing a birthday party. And therefore, I've kind of mainly concentrated on providing the world with convenient, easy to do objective measurements. And I'm hoping that as time goes on, more and more relationships will be developed between the objective and the subjective, like how good is that picture? Quick summary here. I'm not going to spend much time on this slide, but there are a number of image quality factors, and I'll be discussing these individually. And they're analyzed by several of the Imatest modules. These images show the type of charts that are used in each module. For example, the slanted edge for sharpness. Another chart which we use for sharpness and also to look at some signal processing artifacts. The good old Grotag-Macbeth color checker, which is very widely used for measuring color, although we measure a great many other color charts. Step charts, which are monochrome charts that have density steps. Light fall off measures the uniformity of lens and sensor response. It has quite a number of outputs. That you just photograph a blank surface or perhaps a integrating sphere. And finally, distortion, where you photograph a grid and measure lens distortion. We'll get into a bit more detail. Sharpness, in my opinion, is the probably most important image quality factor, although certainly not the only one, because you can have very, very bad sharp images if they're off in color or exposure. This image shows an example of how we measure sharpness. At the top, what you see is a sine pattern. You have an original sine pattern that's modulated sine wave increasing in spatial frequency. Spatial frequency is not familiar to most people, but it's very similar to audio frequency, aka pitch. The better the response at high spatial frequencies, the sharper the image, the more detail you can see in an image. So I'm showing what happens when you blur this case, it's a simulated lens. When you blur a sign pattern, at the high spatial frequencies, the contrast drops. Similarly, this is what happens when you blur a bar pattern. This is the amplitude of the bar pattern that drops off in frequency. This blue line is the envelope of the amplitudes of the sign pattern as you go up in spatial frequency. This response is called the spatial frequency response of the imaging system, or also called the modulation transfer function. They're synonymous in practical cases. When you have a good quality test chart, they're the same. And this is what we use to measure lens sharpness. This is in spatial frequency domain. And the nice thing about working with spatial frequency response is if you have an imaging system that consists of several components, lens, sensor, and then software, sharpening and noise reduction, which do opposite things, the multiple of these, the product is the total response of the system. In spatial domain, you can't do anything like that. You'd have to do a convolution, which is extremely awkward and not terribly enlightening. So this is an example of the Imatest SFR spatial frequency response module. What you see in the image on the right is the unblurred image and an example of a blurred image. This turns out to be expressed, these results are expressed in terms of the spatial frequency response on the left. The black curve is the relevant curve that describes the system. It rolls off in frequency so that at the 50% point is about 0.324 cycles per pixel. I should explain that. There are a number of ways we can scale spatial frequency. Cycles per pixel is a scaling factor that lets you know how efficiently you're using the pixels. This number, 0.324, is typical of a good quality imaging system. The Nyquist frequency, which is a half a cycle per pixel, is the highest frequency at which you can detect real data. Anything above this frequency is essentially garbage or nonsense. It's going to be aliased to a lower spatial frequency. And I won't go into the detail now, but if you're familiar with digital sampling, it's a pretty familiar concept. So what we're looking at is measures of sharpness. And the one that I most typically use is the 50% MTF, where it drops to half the low frequency value. Sometimes I use half the peak value. And that number is very similar to bandwidth, half-power bandwidth in electrical engineering. So it's a good, but perhaps not perfect, number for summarizing sharpness. Now you see I have a dashed red line in this curve on the left. That has to do with something I've done which is called standardized sharpening. And what that is a little algorithm I cooked up that enables me to compare different cameras. I'll discuss sharpening in just a moment, but the key there is that every digital image at some stage in its processing needs to be sharpened. I mean, digital sharpening is one of the key advantages of digital imaging. And lenses and all have roll-offs and MTF, and you can recover quite a bit of perceptual sharpness by sharpening. Cameras have different degrees of sharpening, usually built into the camera. Some of them have severe over-sharpening, which I'll discuss. This standardized sharpening that I do over here, and it's discussed in a lot of detail, essentially normalizes the image. This particular image is actually under-sharpened. It has less than it really should. So that different cameras with different degrees of sharpness have their sharpening either boosted or cut so they can be compared. But it's not a perfect way of comparing cameras. It needs to be taken with a grain or two of salt. But it is somewhat useful for comparing different cameras. Let me talk a little bit about sharpening here. In digital sharpening, what you're doing is from each image pixel, you're subtracting a portion of the neighboring pixels. And that has the net effect of sharpening the appearance of the image. In this case, an edge, such as we use for testing, the black would be the unsharpened image. The sharpened image will be the red. This has a little bit of overshoot, which generally is not visually objectionable. But this sharpened image is going to look a lot better to the eye, and you'll actually be able to see more detail visually in the sharpened image. Of course, you can over-sharpen an image, and that's pretty common with compact digital cameras. And when an image is over-sharpened, you see a peak here. This is the average edge response. So this is spatial response. And you see these peaks in a lot of inexpensive compact digital cameras. And this peak in the spatial domain corresponds to this quite large peak in the frequency domain. I often see peaks of 50% above the nominal low frequency response or greater. The over-sharpening does improve the measured MTF response. So it is a bit of a problem. It's kind of a way of cheating in making digital cameras look good. So in general, one has to say sharpening beyond a certain amount is probably going to degrade the image. I happen to think about 20% is a good sharpening number that maybe you don't want to go beyond, and for some instances maybe less, maybe a little more is suitable. A little bit of over-sharpening definitely does not hurt an image, but over-sharpening is common enough, and it is something we need to be concerned about in measuring cameras. And you do need to, when you develop an imaging system, you need to select an appropriate sharpening, recognizing that there's going to be a little bit of loss in the display device. So you may want to go a bit over the theoretical optimum if you don't consider the display device. Wait a minute. Well, MTF is a measure of the sharpness of a device. One of the things that is of great interest is to relate the MTF, or spatial frequency response, to perceptual sharpness. And in Imatest, we recently introduced a measurement called subjective quality factor, or SQF, that is a perceptual measure of how sharp an image is going to look. This is a measurement that was developed in the early 1970s at Kodak and has been quite used by Kodak and Polaroid, although I just yesterday talked to a former Kodak scientist who mentioned some other measurements. It's not a perfect measurement, and none of them are as far as I know. This was a friend of mine who was a former Polaroid scientist got me going on the SQF measurement. But essentially what it involves is, it's a way of combining the MTF curve of the camera, the eye's contrast sensitivity function. The human eye is sensitive to contrast at spatial or angular frequencies that peak around 6 to 8 to 10, perhaps, well, 6 to 8 cycles per degree. And so very low spatial frequency information you don't really see. It's just a variation in brightness. At high spatial frequencies, your eye can't resolve it. So what's happening in that angular range is important. Of course, now we're talking angular frequency, which has to be converted into spatial frequency to work with MTF. So what we do is we plot this SQF versus image height, making some assumption about viewing distance. And I allow you to pick the assumptions, but I typically assume that the viewing distance is going to be proportional to the square root of the image height. I'm thinking in terms of, say, fine art exhibition prints. You tend to move away from a really big print, but not linearly with a print height. It's just a guess to be able to get a result. And so you come up with a number that plots SQF. The black is for this MTF that doesn't have the standardized sharpening. It's a bit of an over-sharpened system. In fact, if this number is too high with SQF, that's an indicator that perhaps there's too much sharpening and quality may not really be improving. But this is a number that does give a reasonable perceptual measure of sharpness. It's still a number that's unfamiliar to most people, so I'm hoping there will be more development in relating this to user preference. But I know Kodak and Polaroid have done quite a bit of work with it. And curiously enough, Popular Photography magazine. In their lens tests, if you dig deep into their website, you'll discover that they're using SQF as a measurement. I'm not even sure that the people there understand what it is or how it's derived. It's software that's been handed down, but in fact, their numbers are the same numbers that I use in Imatest, except that it's for the lens only, whereas Imatest is measuring the entire imaging system. So that kind of wraps up the sharpness part of the MTF measurement. One thing I should point out is that the image that's used for measuring the sharpness is a slanted edge. And the slanted edge is light to dark. It does a fair amount of processing on this edge so that it averages it. It oversamples it so that you can look at response above the Nyquist frequency. But one of the key things to note is that typically close to edges, cameras are doing a great deal of sharpening. Very typically, if you go away from an edge, the camera will say anything that's here is noise, and it will do noise reduction, which is the opposite of sharpening. It's in fact blurring or low-pass filtering. So the contrast of the edge in real camera systems with this, as I call it, nonlinear signal processing, can vary quite a bit with the contrast of the edge, not because of the sensor or lens. Yes?
You'll probably get into this, but so you're talking about this in a general case, but some cameras do luminosity different from color when they do their sharpening, their smoothing.
Right. Interesting question. I have a little program for printing out these test charts, and you can print them out with any of the primaries as the highlight value. Of course, you can always put a filter in front of the lens. I'm working now with the RGB and the luminance channel, the Y channel, which is the weighted sum, mostly green. I have not done this with the like the luminance and chroma, the two chroma channels, which are not quite uniquely defined. But I do, in fact, in many cases, if you turn off the standardized sharpening, then the three color channels are highlighted, and you can see them clearly and see what's happening there. Or you can, in fact, look at, say, red and black, blue and black, which is generally going to give you quite a bit worse response with a Bayer-type sensor. If you have a Foveon sensor, they're going to all be the same. So there are a number of options in Imatest that let you test out some of the fine details. And one thing that I'm committed to is if you have measurements that you're interested in that Imatest doesn't include, well, I've got the interface and the whole structure ready. It's usually quite easy for me to add options, and I've found ways of doing it that I hope don't clutter the input dialog box too much. And I'm always eager to add more measurements to Imatest to meet everybody's needs. I figure if I make customers happy, maybe I get more customers. Hopefully that works. Okay, now we go on to a measurement that's actually quite closely related to sharpness, and that's lateral chromatic aberration. That is the color fringing that you see near the edges of the image. This is typically something that happens in extreme telephoto, retrofocus, or extreme telephoto or extreme wide angle lenses, the retrofocus lenses, and quite a few zooms. Usually not too much of this is visible in normal focal length lenses. And what lateral chromatic aberration is, as I say, you see it as color fringing near boundaries, like near the mesas here. And in fact, it isn't really simple boundary position adjustments, but there's actually quite a lot of change in the shape of the transitions. This is most pronounced near the edges of the image. Typically, there isn't much of this near the middle, although you might see this if there's some misregistration between pixels. My perceptual measurement of chromatic aberration, which I'm using for now, is the area in pixels between the normalized images. This goes from 0 to 1. It's normalized. Horizontal axis is pixels, so the area is actually measured in pixels. Typically, this increases linearly with distance from the center of the lens, or roughly so, certainly not exactly. So I also have chromatic aberration as a percentage of the distance to the corner. But these are pretty good measurements and lots of detail on the lateral chromatic aberration, which is something that can be corrected in software post-processing. Noise is another very important image quality factor that could be equal or certainly close to sharpness in importance. And that's the sort of graininess. Noise in film was called grain. We just call it noise in digital imaging. It comes from a number of factors. One is simply the number of photons reaching the site. In that case, the noise increases with the square root of the light level. So the signal-to-noise ratio goes down with the square root of the illumination. That's a major factor, especially in very small sensors with small pixel sizes. There's also electronic noise, Johnson noise, 1/f noise, and a whole bunch of other noise factors. So we measure noise in a number of ways. In fact, I've recently enhanced the noise measurements in recent versions of Imatest so that you can get several different definitions of signal-to-noise ratio, as well as noise measured in pixels, noise normalized to the maximum 255 pixel level, noise normalized to a difference between black and white, so that you're kind of normalizing out the contrast differences of different cameras. On the middle one I have, in this case, noise measured in f-stop. So it's a noise that's proportional to the illumination level, or luminance level. I have a great many options, and of course they're all described in gory detail on the website. Yes?
How do you distinguish between noise and signal? When you do your measurements?
Noise, when I'm looking at a patch in either the color checker, I'm usually using the bottom row or the third row or the step chart. What I do is I isolate the patch. The signal typically is the average, the mean level of the patch. The noise is the standard deviation of the level of the patch. But I do a trick before I do that standard deviation. What I do is I subtract off a second order fit to that patch. So that would mean that subtracted number would have a mean of 0. We don't use that. That removes non-uniformity in illumination, which is a big issue generally, from the patch. And I do that subtraction before I take that standard deviation, which is the same thing as RMS, or root mean square noise. So then I take the ratios, and as I'd mentioned, there are a number of ways of defining signal-to-noise ratio. This was a problem in my former field of magnetic recording channels, and the same problem persists in imaging. Whenever anyone mentions signal-to-noise ratio, ask them how they define it, and they probably have a slightly different definition from the one you're thinking of. I've learned that. You just have to deal with that, so I will probably be adding more definitions as people request them. In fact, there's one called PSNR used in video I'll probably add within the next week or two. It's a widely used standard measurements, and there are lots of papers that will explain why it's not a very good measurement. That's why I haven't added it so far, but people want it. Color accuracy is another important image quality factor. And in the color check module, we do an analysis of the Grotag-Macbeth color checker to determine color accuracy. In this case, we're looking at the differences in the AB plane of LAB color space. This is a transformation of RGB that is relatively perceptually uniform and very industry standard, that gives you a fair idea of how far off colors are. And it turns out that distance in LAB space is a very first order way of estimating how wrong or how off colors are. There are a number of other measurements that I describe on the website. They all go by the name delta E for total change in the space, or delta E, which is just or delta C, which is just the change in the chroma. But there are a number of other measurements that are weighted to try to get closer to how the eye perceives color difference. There are delta E 94, delta E CMC. None of them, in my opinion, are perfect. And again, I plan to keep adding options as they become available or I become aware of them. There's a new measure called delta E 2000. It's a bit controversial. I don't think it has a big, it's very complex, so I haven't added it yet. I don't think it has a big advantage over the delta E 94. So there are quite a number of ways of doing this. We also have a new module called multi-charts that analyzes the color in a number of other color charts and allows you to look at segments of charts, different regions, and produces quite a number of displays. In fact, I will show you a little bit about that later. Okay, more image quality factors, tonal response and contrast. This is one where there's no good or bad. Oh, one thing I wanted to mention about color before I move on. Accurate color is not always pretty color or color that users prefer. Sometimes users prefer distorted colors, like they like skies that are bluer than the cyan that's typical and more saturated. They like grass that's greener, more cyan, less yellow than real grass. People tend to like more saturated skin tones, and there's some cultural differences where, as I understand it, Asians tend to like skin tones cooled a bit. Europeans, North Americans tend to like them warmed a bit. So we all end up looking sort of close to each other, which we sort of do anyway, when we do these adjustments. So depending on markets, people may want to make the algorithms for color or the reference values, which you can change, a little bit different. Tonal response, it's a pretty important area that relates to image quality. And again, perfect tonal response may not be desirable. You do want to see what a camera is doing, how it responds to the tone. For that, we use the step chart module, which analyzes these step charts that have constant density steps. The tonal response is shown here on a log plot. The average slope in the highlight to center region is called the gamma. Gamma is pretty much the same thing as the contrast of the image. There's an encoding gamma, which is usually around 1/2. There's also a display gamma. That's 2.2 for sRGB is the standard for the internet. There's a slightly different standard for Macintosh computers. But this does tell you the camera's response. Typically what you see in cameras is in the encoding side, there isn't a pure S-curve. You typically get a roll-off near the highlights. This is, for scientific accuracy, not so good, but for pictorial quality, a very good thing, because if you have a true linear response, you tend to burn out highlights very quickly. They go pure white, all 255s, and this does not look good in images. So this type of shoulder on the response curve over here, on the upper right of the curve, that's what you get in film. And I think it's a desirable thing to have as a part of your image processing chain. In digital processing, you see it in most of the better cameras. Dynamic range is another important issue. In fact, in digital SLRs, dynamic range is extraordinarily good. I think in ways better even than negative film, and way, way better than slide film. That's the range of exposure that a camera can respond to and produce an image of a reasonable quality. So we measure that using a transmission test chart. This is an image of the Stauffer T4110, very inexpensive chart that you can buy. And there are other charts, like from Image Engineering. They have a chart that has a circular pattern that is definitely a finer chart and a lot more expensive. And we analyzed both of those charts, and they show the response over a wide range. Now, the dynamic range is the range of exposure, and I usually use f-stops, which are factors of 2, to measure the dynamic range, whereas 3.32 f-stops are 1 density unit. That's a log 10 based unit. But the dynamic range is defined at quality level. That is where the signal to noise ratio is better than a certain amount. So this particular curve, which is for a Canon, I think it's an older Canon that doesn't have too many pixels, so it has fairly large pixel size, an older G2 compact camera. It's quite a good dynamic range. It's 9.75 f-stops at medium. I'm able, or the customer of mine was able to actually detect 9.8 f-stops. Medium dynamic range means that the f-stop noise is, what is it, less than 0.5 here. What are the units? So the noise is less than half an f-stop, essentially. High quality is noise less than 0.1 f-stop, and at high quality, this old camera has a 6.83 f-stop dynamic range, which is really very good. It's a lot better than slide film. In fact, there has been a tendency in a lot of cameras, and especially in camera phones, to make everything compact, which means shrinking the pixels. You tend to get a lot more noise when you do that, so the effective dynamic range at any given quality level tends to be fairly low with some of the newer cameras. Well, to get around that, people do a lot of signal processing that can be remove quite a bit of detail. So there are people I know who really like the older digital cameras with those big pixels. Of course, a DSLR has big pixels, big cameras they are, and that's what I like to use for my own work. Lens flare is another very important issue, and it's especially important for some of the applications like yours where you don't have controlled lighting. That image I showed of the Boulder NIST laboratory, you had the predominant light was very much behind the subject, just off the axis of the camera. In those situations, light that bounces off the lens elements or the barrel on the inside of the lens can fog the image. That fog is called veiling glare or flare light. And that's a fairly important thing to measure. There's also ghost imaging that you can have. Ghost images are kind of non-repeatable. They're unique to each lens, and so I'm not attempting yet to measure that. But to measure the lens flare, and this is like a typical flare type of thing that you'd get, what I do is, it's a part of the step chart module. I measure Kodak Q13 grayscale, and I have this black hole, as I call it. It's actually a cavity lined with black felt that no light reaches directly. So this is really true black. And I measure that after I use the results of measuring this chart to linearize the image. I measure the veiling glare or flare light is the value of luminance in this black hole compared to the white region. And that's typically around 0.2 to 0.5%, and definitely is something that depends on the lens quality. And the really fine lenses with excellent coatings are going to have low flare or veiling glare levels, and cheap lenses may have high flare. Yes?
Isn't that dependent from the illumination source? If you are shooting against light, that's much more prone. So how do you factor that in your measurement?
I just remembered to repeat the question. Okay, how do you factor it into the measurement if the illumination source is near the image? There's so many possible ways of doing it that I've had to make a simple approximation. I'm really not dealing with the illumination source, but what I'm doing is in this target, this is in the central part of the image, but I try to make it so that the white background, I mount the Q13 on a white background. Normally when I'm testing things, I'll do it on a gray or dark background. And I try to make the white background extend out so that the area goes well outside the image frame. Hopefully something equal to the image frame on the outside. That's pretty hard to do with a wide-angle lens. And the assumption there is that the fogging part of veiling glare is sufficiently high that this will give me a fairly consistent and usable number that will give you some indication of what happens if you have a light source outside the image. But it's not perfect, because when you do have a light source, especially if it's a bright, narrow light, you're going to get the ghost imaging. And the thing about ghost imaging is that's so variable with different lenses. You just have to try out different things with your lens that's under test. There is, as far as I know, no industry standard for this, because almost any company will be able to make their lens look good in some way and other lenses look bad by setting up a test setup just so. So it's one of those tricky things. You just have to try to figure out what the conditions of use for your lens are and maybe set up something there that becomes your own internal standard. My way is have a big piece of mat board, make it go way outside the image. Hopefully that answers it, yes?
So when you measure that, you also have to measure the black level or like the difference, and to quantify that as a percentage, you also have to linearize the response. So how hard is it to get the black reference and the linearized response?
It's pretty easy, because I'm measuring it right next to the Kodak grayscale. I can use that to linearize the response. What I found is that almost all cameras that I've seen, their electronic response is fairly linear as you go down to the low levels. So I'm crossing my fingers a little bit here. But yes, I use the grayscale to linearize the response, and then I measure inevitably much darker in the black hole than in the 1.95 density patch 19 here. Ooh, reference image with lights turned. There we go. Good question. No, I don't have a reference image with the lights turned off. Let me think about that one. I could do that to see what the basic fogging is. This is essentially a relative measurement. Right now, basically, I'm linearizing with a grayscale. This is something to think about, something I may want to add. What is the zero level when you turn off the lights? Pardon?
You linearize first without the white background with a different chart and apply that?
No, I linearize it for the image under test. And one of the reasons is if you do a different exposure, you're going to have a whole different set of conditions. You may have different amplification. Many cameras have adaptive signal processing. So I use this grayscale for the linearization. And then I extrapolate down to zero, hoping that I get a reasonable number. What I do get in practice is if you're testing different lenses or different lighting conditions with the same camera, you will get a very accurate relative measure. I can't promise you that it will be an absolute measure that might be the same with a completely different image sensor. But it is a very good relative measure, because this is the best way that I know of to linearize the image for this test. And we can discuss it later. Exposure accuracy is based on a couple of assumptions. That when you're using a reflective step chart, the white area has a reflectance of about 90%, and in the so-called theoretical ideal exposure, if you have linear, a pure gamma response, 106% will saturate the image. So I do a bunch of math, and I use the results from either step chart or color check to estimate how far off your exposure is. This can be useful if you have one of these charts in a scene where you have an auto exposure algorithm and you want to see how well the auto exposure is working. Light fall off is a module that you work by simply photographing a plain white or gray surface. The perfect thing would be something called an integrating sphere, which is a bit expensive. Or you can go to Home Depot and get a globe for a lamp that might be the really cheap integrating sphere if you figure out how to light it right. And this measures lens vignetting, lens fall off. In recent months, I've enhanced the light fall off module to measure all sorts of non-uniformities in sensors, like local noise variations, and quite a number of things. It produces quite a number of displays showing how uniform your response is. So it started with lenses. It keeps going on and on as people make requests. Lens distortion is the barrel or pincushion effect that particularly wide angle or ultra wide and zoom lenses tend to have, and that's important for architectural photography and such things. For a lot of types of photography, it's not very important. Very important for astronomical photography. Lens distortion is something that can be corrected quite easily in post-processing. And I come up with a number of different coefficients that you could use, like third order and fifth order. And also I measure lens decentering with a distortion module. I have these backwards. One of the really interesting phenomenon that I've been looking at recently, and this is a module that's up on Imatest now, but I still call it a beta because I haven't finished the documentation, is I'm very interested in the signal processing and how in high contrast regions you get sharpening, in low contrast regions often you have noise reduction or low pass filtering. Sharpening is sort of high pass, a high frequency boost. So what I've done is I've created a chart that can be printed with the Imatest test chart modules that has, varying spatial frequencies on the horizontal axis, and this is a sine wave pattern, and varying contrast or contrast squared on the vertical axis. And I'm looking now at the normalized MTF. I normalize it to 1 on the left. I have many displays that I can do as a function of the image contrast. Now if I go back, this is a very good Panasonic compact digital camera with a Leica lens. I got it from my wife so I could steal it when I want a compact camera. And at ISO 80, what you can see here is that it has quite a bit of sharpening at the high contrast levels. The sharpening gradually diminishes, and the contrast at, or the MTF at low contrast falls off. But now if I go to ISO 800, it's quite different. There's very little sharpening, even at high contrast levels, and things drop off much more quickly. This is one of the things I've been quite interested in lately. This chart also can be used to measure color moire, which is an issue in some cameras. Colors that appear because of the aliasing effect if the lens is too good for the sensor. So this is a new module that I've recently added. And what I've done now is I've covered the key image quality factors. We're running out of time anyway. I'm going to take a quick spin now. If I have a minute or two left, I hope to take some questions, but a quick spin through the modules. So we have step chart that measures either transmission or reflective step charts for tonal response, gamma, which is contrast, noise, dynamic range for transmission charts, and exposure error. We have the color check module that uses the Grotag-Macbeth color checker that measures color accuracy, also tonal response, gamma, noise, and exposure level, although with a bit less detail than the step chart module. A new module, relatively new, called multi-charts, works with a number of different test charts. It has a highly interactive interface and produces quite a number of displays, including a rotatable 3D display of color errors. In this case, we show it analyzing a portion of the IT 8.7 chart, which is an inexpensive chart used fairly widely, but I support quite a number of different charts, including the color checker SG. Distortion and light fall off, we've discussed. SFR, we've discussed again. SFR works with a slanted edge image and produces results for both the average edge and the MTF. So this is spatial domain, frequency domain. Produces a lot of summary results that hopefully relate to perceptual image sharpness. And the final summary is image quality consists of a number of factors. Imatest analyzes a whole bunch of them. When I figure out how to analyze additional factors, I tend to add them as I have time to add them. The key thing to think about in relation to these factors is, some of them are primarily affected by capture. Some, such as white balance, are mainly post-processing. But of course, you have to get the capture right if you are to have the material there to work with in post-processing to bring the image up to a high-quality image. The weighting that you give to each factor, or the importance, really depends on the application and the user preference. So that's something that you have to think about, what works for your application. And it is difficult to define single measures of image quality. It's kind of a holy grail that we may not really get to, but it's something that at least I'm trying to come up with more simple measures of how good things look. So that's the end of the talk. I think I have about 2 minutes. Are there any questions?
Can you go one slide back?
One slide back.
Yes. So what do you try to explain on those graphs when you have overshoot and undershoot on the first graph?
Okay, on the overshoot and undershoot, what am I trying to explain? Okay, the black curves here are the actual response of the system. The dashed red line is with what I call this standardized sharpening, meaning a way of normalizing different cameras. If I define what I consider to be over-sharpening and under-sharpening, and that involves just basically the response at a third the Nyquist is the same as the response at 0 frequency.
But isn't that like a direct consequence of chopping off higher frequency elements like Fourier transport? And you always get those undershoot and overshoot.
Okay, the question is this a response of signal or a result of signal processing? I cannot measure the intrinsic response of a system without signal processing. So there's always signal processing involved, which may result in overshoot, or the signal may be undersharpened. There may be very little. So what I've done with a standardized sharpening, which I often don't use, is I've just normalized it. I sharpen undersharpened images. I cut down oversharpened images. It's merely a way that allows you to compare different cameras. If you're measuring your system, you probably want to click the button that turns off the standardized sharpening, and then, forget about it. It's usually like for people reviewing cameras for magazines, so they can compare different ones, have some basis. Not perfect, mind you, because you can hide anything with signal processing, and I'm working on, learning what the signal processing is doing. Anything more?
Can you analyze systems that make use of fisheye lenses?
Fisheye lenses are kind of tough because of the extreme distortion. You can measure sharpness in the center of a fisheye lens, but I'm not going to do very well at the edges. The slanted edge algorithm actually removes second order fit. Second order curvature from the image. So a little bit of curvature won't adversely affect the MTF, but a lot of the measurements are going to have trouble with fisheye lenses, so you have to linearize them first. But you can work in the center for noise and a few of those details. Or you can use the circular patterns. There's a chart, some circular test charts that will work with fisheye lenses. Any others?
Can you discuss the Siemens star chart, which is a circular pattern?
The Siemens star chart is a star-type circular pattern. I plan to add support to it in a month or two as I have time. Okay, I think our time is up. So thank you very much.